Welcome to the class of NN, that is neural networks. In today's lecture we will be seeing the models of the neuron. There are three models of neuron that are classically classified, that is McCulloch-Pitts model, Perceptron model and the Adaline model. As you already know, the structure of the neuron, which consists of the inputs, the weighted functions, the summing part and the activation unit, and finally you get the output. Okay, now in the McCulloch-Pitts model you have the inputs A1 to AM, weights from W1 to Wm, and you have the summing part, then the activation value, that is the activation function, then finally you get the output, which is the function f of x. Now in the McCulloch-Pitts model, the output signal S, here we denote the output signal with S, is a typical non-linear function of f of x, that is of the activation value x. Now the two equations describe the operation of the McCulloch-Pitts model, abbreviated as MP model, that is the first one is the activation and the second one is the output signal. So here the activation value x is given by summation from I is equals to 1 to m multiplied by the weighted function and the inputs minus theta, that is the summing part, and the other one is the output signal which will be getting. So in the MP model, three commonly used nonlinear functions are there. The three nonlinear commonly used functions are binary, ramp and sigmoid. You can see the binary, which is a normal line. With the response itself you can observe it. The second is the ramp and the third one is the sigmoid. The ramp has an inclination which represents the behavior of the ramp signal, as you already know, and the other one is the sigmoid, similar to a ramp signal, but it moves from the left quadrant to the right quadrant with a much more higher elevation part when compared to the ramp signal. Now using the MP model we will be trying to illustrate you three examples, that is the logical examples. The first one is the NOR gate example, second is the NAND gate example, and the third one is the memory cell assuming unit delay for neuron. Now as you already know, what is a NOR gate? A NOR gate is nothing but the output of the two values added with a bar on it, that is the output gets inverted because of the bar. So here you have two inputs A1, A2, and the output over here is S, and all the possibilities, that is 0, 0, 0, 1, 1, 0, 1, 1 are being implemented so as to get the required outputs. So here the inputs are being taken and here it has been summed up, and here you get it inverted and here you get your output. Now similar way the NAND operation is also done. In the NAND operation, here you get the output of the two inputs, which is the multiplying of it with a bar of it, so it gets inverted at the end. So all the possibilities and the results are being over here. So here you can see with respect to the NAND logic how you are getting the output. Now coming to the memory cell assuming unit delay for neuron, and an initial excitatory input 1 sustains the output 1 and initial inhibitory input plus 1 sustains the output 0. Means for plus 1 you will be getting 0 and for 1 you will be getting 1, for which you get your output S. So in the above MP model, binary output function is used, that is f of x is equals to 1 if x is greater than 0 and f of x is equal to 0 if x is less than or equal to 0. Now in the MP model, a single input and a single output MP neuron with proper weight and threshold gives an output a unit time later, means 1. The unit delay property of the MP neuron can be used to build sequential design circuits with feedback. So you can also develop feedback circuits. It is also possible, which you can see in this example also. It is also possible to have a memory cell. This example only is illustrating to you, which can retain the output indefinitely in the absence of any input. So storing capability is also there. In the MP model, the weights are fixed, means you cannot change. Hence, a network using this model does not have the capability of learning. Moreover, the original model allows only binary output states operating at discrete time steps. So this is the drawback of it, that it does not have any learning capability because the weights cannot be updated. Now coming to the second model, that is our Perceptron model. The Perceptron model is basically Rosenwald's model, the scientist who has done this particular model, so it's been named after him. So this is a model for an artificial neural network which consists of outputs from sensory units to a fixed set of association units, the outputs of which are fed to an MP neuron. Now here you have the sensory units which are being associated to the association units which are taking the input, then the remaining process is being continued, that is going to the activation unit, then to the output unit. So here the addition what you have here is that instead of giving the inputs A1, A2, A3, these are being taken by the association units from the sensory units. So this is the addition, or you can say, and development over the MP model. So these are the equations which you have in your Perceptron model. So you can easily understand the MP model. Then the upgradation of the MP model is nothing but the Perceptron model, where you have the sensory units. Okay, now we'll go to the third model, that is the Adaline model. Adaline is an adaptive linear element model. It is the full form of it also. It is a computing model proposed by Withdraw. Now the main distinction between the Perceptron model and the Adaline model is that in the Adaline the analog activation function is compared with a target output B. In other words, the output is a linear function of the activation value. The equations that describe the operation of Adaline are as follows. So it is very much clear that here the difference comes in the activation value. Earlier in the two models, or it can be easy to say that the two models are the understanding point of view one model, because there is only a development of the sensor unit. No doubtly other processes are also changing in the Perceptron model with respect to the MP model, but to understand it we can say that it is a one model. It is a one model in which you have the sensor units, then you have the continuity, and you get the outputs, where the output required is obtained with the help of the activation value. But in here you are comparing the activation value with respect to the output value, and the relationship is over here linear. Okay, remember this part. Earlier the relationship was non-linear. Okay, so this is the activation function, output signal of it, the error, and the weight change. And one more thing what is here is that here you have weight change of 76 input with respect to the input, and here you have eta delta AI of weight change. Okay, so this was about the different types of models of the neuron. Thank you.